Good morning and good afternoon and good evening, ladies and gentlemen. Thank you so much for taking time out of your busy day to join us on our call, BGAN Satellite Communications in Software-Defined Radio. My name is Jeff, and I'll be your host for today's event, which means I'll be in the background, helping you with any technical questions that you may have. Now, if you have a technical question, please type those to me in the chat area that you see on the right-hand side of the screen. If you have a question about today's content that's being presented, please type those questions in the lower right-hand corner in the Q&A box. Once it's typed in the Q&A box, simply type or hit send or submit. It will go directly to myself and the team of panelists here this morning, who will gather all questions and then respond to those questions at the end of today's session. The event is being recorded, and without further ado, it's my privilege to turn the call over to your moderator today, Catherine Borthwick. Catherine, the call is yours.
Thanks. Good morning, everyone. Good afternoon. Thank you for joining us today for our presentation, BGAN Satellite Communications in Software-Defined Radio. Today we'll be featuring two speakers. Our first is Klaus Vesterholt from the Danish software company Gatehouse. Klaus is a technical program manager for satellite communications at Gatehouse. Throughout his career, he has led a number of programs and projects in communication software for wireless systems, specifically GSM, GPRS, and Inmarsat BGAN. Klaus has a master's degree in electrical engineering from Aalborg University in Denmark. Our second presenter, Cyrus C., is a manager of business development here at Spectrum Signal Processing. He has more than 10 years of experience at Spectrum in a variety of different roles, including applications engineering, technical marketing, and business development. Cyrus received his Bachelor of Applied Science degree from Simon Fraser University here in British Columbia. We'll begin our presentation. Again, please feel free to use the Q&A section on the right to type in any questions you may have during the presentation. I'll pass over to you, Klaus.
Thank you very much, Catherine, and a welcome from me as well. I'll be doing the first part of this presentation today, talking about the waveforms, the software we provided, and a little later, Cyrus will be taking over to talk about the hardware aspect. Let me start by showing this very simple example to give some indications to the benefits that comes out of software-defined radio in general, and also what it really is. This simple example is taken out of a military context. If we take a look at how typically multiple communication standards are supported today, this is being done by having several platforms installed in the vehicle. BGAN can be one of them. There can be other waveforms as well. So this occupies quite a lot of space in the vehicle. It's not very flexible, and it's a stovepipe kind of system. And now, if we go into the SDR world, software-defined radio, if we install a software-defined radio platform in the vehicle, then this platform can be configured as needed, as required for the particular mission that this vehicle serves. So we want to provide a solution where BGAN can be loaded on a software-defined radio, and this platform can then load other kinds of waveforms. So this is a much more flexible solution, and using a single platform, space is safe on board the vehicle. Now, this next slide gives a little more background for the use of satellite communication. We're going to continue in the military context. A SatCom communication link in general can provide an improved interoperability. So it allows you to be able to connect with your network servers no matter where you are. So it provides you with an independence of the geographic location. So the SatCom can be used and is being used as typically a backup capacity. So on short ranges, there are HF, VHF, UHF communication, but on longer ranges, these are not usable anymore, and SatCom is then there to serve as a beyond line of sight backup ability that gives constant connectivity. Now, we're going to look today if there is a simple way to include SatCom, and in particular our BGAN product, in a communication portfolio, commercial or military, without any equipment taking use of SDR platforms. But before we continue, I'd like to give a little background on Gatehouse. Gatehouse is a Danish company. We provide technical software, typically embedded communication software, and also system engineering expertise. We were established in 1992 with about 60 people, working within different business areas. The one which is relevant for today's presentation is our satellite communication business area. In this area, we've been working with Inmarsat since 1999. And we are well known in the Inmarsat world as the supplier of BGAN protocol layers for the largest part of the BGAN terminals which are out on the market today. And we're also supplying BGAN testing software. We've supplied our protocol stack software for the last approximately 10 years to 8 terminal manufacturers. There are actually 23 products on the market approved by Inmarsat today with our software in them. We're working with software-defined radio since 2007. Let's spend a little time to give a little background on Inmarsat. Inmarsat is the largest provider of mobile satellite services and uses geostationary Earth orbit satellites to provide coverage on the globe, except for the polar regions. Inmarsat has been in the business since 1979 and has been developing several generations of satellites. BGAN is the latest high-rate service from Inmarsat, and the 10 service required estimates from Inmarsat in a new fleet of 7 satellites. It's being served by Inmarsat 4 satellites. It requires new satellite access stations and a range of new terminals to serve different segments of operation. I'm going to come back to that on the next slide. BGAN as a service began operation in December 2005, where the first 2 satellites became operational, and a satellite was operational since January 2009, and this gave global coverage from that time. This is a picture showing the coverage of the Inmarsat Broadband Global Area Network of the Inmarsat BGAN service. You can see there are 3 satellites which covers together the globe, except for the polar regions. There are a number of access stations, one in Hawaii, and about 2 other access stations placed in Europe. Serve the users in different segments. Several terminals have been developed by different manufacturers. And there are terminals specifically designed for land portable use. So this terminals which must remain stable while being used. There are other kinds of terminals that can be installed in vehicles to supply BGAN communication on the move, motion. There are other kinds of terminals that have been designed to be installed on board ships, and also a group of terminals which are used on airplanes. If we take a brief look at the services that BGAN provides, it provides a data rate capability, actually an IP connection over satellite with up to 492 kilobits per second, and then the receive direction simultaneously. It also provides a guaranteed bit rate, a streaming service, data rates up to 256, and recently actually 384 kilobits per second, being used by, for example, the media. It also provides voice, provides text messaging services. Let's look at the way the classical architecture for a BGAN terminal today. A traditional terminal is built in a way that the BGAN specifications are incorporated in the hardware part and in the software part. So typically the hardware part is being developed specifically for the BGAN service and comply with BGAN specifications. So that's in terms of filters, bug frequencies, processing capabilities, and so on. On top of the hardware, there's of course a software, and Gatehouse protocol stack is part of that to most of the terminal. Now, what we have been developing in cooperation with Spectrum signal processing is a waveform that contains all the BGAN functionality in software, which we have been ported to the Spectrum platform. So this actually enables a new architecture, software-defined radio architecture, where we can build a BGAN terminal based on a more generic software-defined radio hardware platform and supplying all the functionality and software. Now this slide provides a little more details on how this waveform is structured. So lower part here we have the Inmarsat air interface, which is optimized to work on a satellite link. Split in two, one part is implemented in the physical layer and one part is implemented in the lower protocol layers. And that is a UMTS access stratum, which provides the three services for packet switch and circuit switch communication. The third part of the waveform is the BGAN application framework. That contains a basic layer of functionality that enables you to build any kind of applications that you need to have as part of your terminal. The BGAN application framework itself provides enough functionality to build a basic terminal. One interfaces out of the waveform. One is a USIM interface to be used for service provisioning. One is a navigation or GPS interface to get the location of the terminal which is needed to operate the terminal. An interface for ciphering, and also an interface defined to communicate with an antenna for antenna pointing purposes. The right side of the figure here, we have more system type interfaces. The waveform runs on top of an operating system. It requires non-volatile memory and also interfaces for trace and debug purposes. Interface here to provide an interface to circuit switch functionality, for example, a voice codec or an ISDN stack. Now we've been trying to look at the requirements that are in place coming out from manufacturers of terminals and radios to be able to integrate our BGAN waveform. These requirements are listed here. First of all, we've tried to build a product which is easy to integrate. So we've tried to build a product where the porting effort is minimum and in general non-complex. We've also tried to build a product, a waveform, which provides flexibility in addressing customer requirements. So first and foremost, this means that the waveform can be configured for the specific class of operation required. There are many different classes of operations for the different segments which I described before, for aeronautical use, maritime use, or mobile use, and so on. It must also be possible to load the waveform and unload it to be able to load other waveforms on board the platform. We've also been trying to build a product that enables the manufacturer to have reduced risk and reduced time to market. And this primarily marketed as we are able to provide all the BGAN functionality. So there's only a limited need for building up BGAN competencies for our customers. We've also tried to supply a solution which decreases the cost of ownership and to have a product which can be maintained, where we can have simple bug fixes and upgraded. It's a software-only solution, which by definition enables more simple bug fixes and upgrades in many aspects. This is about the waveform complexity. It's being part of this presentation just to explain that the BGAN waveform is highly optimized. It's highly optimized in terms of the bandwidth it provides, the capacity it provides, services, the different kinds of services it provides. So it's not a simple point-to-point waveform, but a very complex waveform. And in our experience, it takes more than 9 years to implement a waveform like BGAN. A number of additional expenses on top of that, test equipment, certification, type approval, field campaigns, and so on. Now the next 4 slides shows in a number of steps how the waveform can be ported into a platform. This shows here actually are the steps which we followed to port our platform onto the SDR 4000 platform from spectrum signal processing. But that would be applicable to port the waveform onto any platform. The first basic step is to evaluate and select a platform. I selected the 4000 family, and in particular the 4021 software-defined radio platform. Now, this platform is a baseband platform, so there's no L-band RF part on board yet. So we had to select an L-band up and down converter, and we selected a COTS, commercial off-the-shelf unit for that, for a prototype. We also had to select an antenna, and we selected a SatCom, which is another Danish company, a class 10 antenna. Now the next step 3 was to write code for the interfaces out of the waveform, which I showed just before. And we wrote the code necessary to interface to the operating system, which was Integrity, on board the platform. We wrote code to interface with the antenna to be able to communicate with the antenna, pointing to make sure that the antenna is in lock and so on. We wrote interface code for the SIM card reader, and also as the last of the main interfaces, an interface to be able to control the up-down converter. Having this code in place, we were able to build our GPP, our DSP code, and our FPGA images. And the first step then was to load the executable code and to check the boot up sequence. So let's write the code to the platform and just to make sure that it's actually working as a software system. So at this step number 5, there's no BGAN functionality activated yet at that time. It's just a matter of sending an AT command to the platform and see that it responds with an OK. Now we have as part of our product a physical layer simulator. And when you go to a platform, that's the first step to be able to verify the BGAN functionality, to actually use the physical layer simulator instead of the real physical layer. Physical layer simulator enables you to run protocol test scripts, basically running on the microprocessor on the GPP, up against an Inmarsat protocol tester to test the protocol that the communication layers are running properly. As a step, the physical layer can be activated, and it's possible to start to receive bursts from the BPLT and the BNE. The BPLT is the BGAN physical layer tester, and the BNE is the BGAN network emulator. Going to the next slide, being able to receive bursts from the BPLT with signal acquisition, and then we can start transmitting bursts back to the BPLT and the BNE combination. Having that in place, we're able to execute Inmarsat's mandatory test requirements, and we add to obtain a preconditional case approval from Inmarsat, which is the first basic approval level. So the MTRs is the suite of test cases for the physical layer and for the protocol layers. The physical layer MTRs test that we transmit in band, and we're testing with the right timing and using the right power. We were able to, with this same setup, to test for high symbol rates to test the maturity of the solution, stability, and the performance. Now this is basically the bench setup, and as step number 12, we were able to point our antenna, our system, towards the satellite and start receiving data. And having that in place, sequentially perform registration, attach and context activation, and then doing on-air testing with the system. And we're using simple FTP application to be able to test the stability and the data rates and the performance on air. Now there are certain basic requirements to be able to host the BGAN waveform on a given platform. We're importing our protocol stack and application layers on a number of different platforms and GPPs. And it requires a system with more 300 MIPS to run a full bandwidth terminal to be able to cover all the different classes of operation. We require 32 megabytes, preferably, for RAM and our code occupies 8 megabytes of flash. On the fifth layer, we run FPGA, and on board the Spectrum platform, we've been using actually 2 FPGAs out of the x64 family, an SX55 and an LX60, with approximately 100,000 logical cells. The DSP side, we need a 16-bit DSP. We're currently using a Texas DSP. We're programming this DSP in C++. We need a compiler to support that, and DSP must have 1 megabyte of dedicated memory with it. On this part, as I said before, we selected a COTS L-band converter, but in general, our part needs to support BGAN carriers, which are placed around 1.6 gigahertz. It needs to have sufficient power and receiver sensitivity to be able to interface with the antenna. The antenna in our case was an active antenna with a built-in LNA and HPA. We're sampling the entire L-band, the MSS L-band, which is 34 megahertz, at our IF frequency, which is 70 megahertz. We need at least 12 bits ADCs and DACs to have the sufficient resolution on our signal. We're using currently 14-bit ADC and DAC. And the system must operate in full duplex, because we have in BGAN concurrent operation of the transmitter and the receiver. This is my final slide before Cyrus will take over more in details on the hardware part. The slide is the mapping, how we're implementing different elements of functionality onto different processing elements. So on the top line here are different processing layers, and to the right side we have the different processing elements, GPP, the DSP, the FPGA, and the headers and the analog hardware part. So if we start at the left-hand corner, we have implemented the IP stack and the air interface stack on the GPP. So that runs entirely on the GPP together with the application layers. We have below that with the MAC layer, below that which runs on the DSP. When we go to the channel coding part, shown here, we run the interleaving and encoding on the DSP, and we're actually running the decoder on the FPGA, which is a turbo decoder. Going to the modulation and demodulation part, we're implementing the modulator in the FPGA. Most of the demodulator also in the FPGA, except for certain algorithms which runs on the DSP. This here is deliberately shown to cover both the DSP and the FPGA, because we are aware that we need to have some flexibility there to be able to address different platforms with different configurations with DSPs and FPGAs. We have to address that, as we have most of our algorithms implementing FPGA also in a DSP version. Now we create our IF signal directly out of the FPGA, our 20 megahertz intermediate frequency. We have our ADC and DAC converters. And on the analog side, we have the before mentioned I filter. We have our COTS converter, and with our active antenna, which hosts the HPA, the LNA, and the duplexer. And now I'm going to hand over to Cyrus.
Thank you, Klaus, and good morning and good afternoon to all. Before I move on and talk about the front-software aspects of an SDR waveform, I'd like to say a few words about Spectrum. Spectrum Signal Processing was established in 1987 and is headquartered in Burnaby, BC, Canada. We have an office in Washington, D.C., and have a total of 57 employees across the company. Our parent company is Decima Networks, and Spectrum offers a wide variety of products and services for communications, equipment manufacturers, and system operators in both the defense and commercial industries. Our capabilities are diverse, from designing and manufacturing high-density processing subsystems to integrated turnkey systems. And some of our customers include the likes of Q Network Systems, Agilent, Harris, and General Dynamics, many of the Tier 1 and Tier 2 system integrators and communication equipment providers in the industry today. Let's starting by looking at the high level of requirements of a software-defined radio or SDR hardware platform. And it very much depends on the perspective you're looking from. As a general or radio manufacturer, your goal is typically to leverage or use the same hardware components for as many terminals or radios to drive down your unit costs and provide economies of scale. You want to reduce your time to market and simplify delivery of software updates and bug fixes. And finally, you want to support both legacy and advanced waveforms or protocols on the same hardware platform. From the perspective of a network operator or systems integrator, your goal is to let customers get the most out of their hardware investment, extend their equipment life, but at the same time, have the ability to add new capabilities and enhancements as the standards evolve. Second, you desire a means to do this quickly and easily, transfer loads rather than an expensive hardware reset. Another requirement is the ability to change how frequency spectrum is utilized. They are using it more efficiently to adapt to a changing RF environment. SDR hardware platform can help meet these requirements. And in the slide ahead, I'd like to tell you a little bit more about how this is done. If we stack and look at sort of a 10,000-foot level, let's start by looking at the definition from the Wireless Innovation Forum for a software-defined radio. Software-defined radio is a communication system where some or all of the physical layer functions are implemented in software. In the slide, we illustrate the key elements of the SDR hardware architecture. So from left to right, some of the key architectural elements include an SDR transceiver, which can operate at one or more RF bands. This front end connects with a flexible analog RF interface that contains the analog to digital and digital to analog conversion. The analog stage then interfaces to a chain of one or more reconfigurable processing elements. Typically, there are FPGAs, DSPs, or purpose processors. Another key element in this architecture is a reconfigurable data flow, or flows between the processing elements and a separate path for waveform, setup, and control. Another key piece is a software communications architecture, otherwise known as the SCA. This is something we'll briefly discuss later on in the presentation. So let's examine the key architectural elements of an SDR platform. An example of a commercially available SDR hardware platform is Spectrum's SDR 4021 software-defined radio transceiver. This is a self-contained IF to Ethernet transceiver that can interface directly with external RF front-end units. Within the external interfaces, we can see two analog IF inputs, an external reference and sampling clock input. There is also an external Giga Ethernet port for all your payload data, and a set port for configuration and debug tasks. Essentially, we can see a lot of the elements of a software-defined radio platform, including your IF, conversion, Talent Vertex 4 FPGA, Texas Instruments C6416 DSP, Freescale 541 general purpose processor. Now, all these reconfigurable processors are connected by a high-speed data fabric represented by crossbar blocks and arrows. There's a separate PCI control and setup path running through the PCI bus interface. Of course, there are other peripherals such as memory and general-purpose I/O to support the waveform processing and the requirements. As I mentioned, all of this is self-contained in a 1RU 19-inch rack-mount chassis with a built-in power supply. The table here lists some of the key specifications of the SDR 4021 hardware platform that was used by Gatehouse for their BGAN development and demonstration. It is worth pointing out that the SDR 4021 is actually built using modular cards. In the case of the 4021, it consists of a baseband processing carrier card along with a menu module for the analog I/O and IF processing functions. What this means is that different hardware configurations may be quickly built to meet a diverse range of requirements, such as differing sampling speed, bit resolution, larger or smaller FPGAs, or DSPs. So we just spent a bit of time looking at the hardware platform, and so let's take a look more about the software operating environment for an SDR platform, specifically specs for SDR 4021 platform. At this level, we have waveforms. In many cases, more than one. These waveforms consist of application components that run on FPGAs, PowerPCs, or DSPs. Examples of these components may include a digital down converter implemented in an FPGA, a modulator core implemented on a DSP. At the extreme case, waveforms or application software may interact directly with the hardware through a real-time operating system running on an embedded processor. In this case, it's the Greenhill's Integrity OS, the associated TCP/IP stack. However, in most cases, the waveforms or application software interact with the hardware through other layers of software. The first layer is the hardware abstraction layer, otherwise known as a HAL, in which SatCom calls QuickCom. This abstracts much of the low-level functions that developers use on the platform in an easy-to-understand application programming interface, or API library. These functions may include reading and writing to registers on an FPGA resource, reading to a high-speed link over a bus, or seeing and receiving signals or interrupts between processing elements. Another key element of the software stack is the SCA, or the Software Communications Architecture. This communications architecture is an open application framework. It is a framework that tells radio developers how elements of hardware and software operate together within a software-defined radio. The SCA is a key element of the U.S. military's Joint Tactical Radio System, otherwise known as JTRS. It defines the structure and operation of the JTRS radios to load and unload waveforms, to run applications, and networked into an integrated system. The primary goal of the SCA is to maximize waveform interoperability and portability between the radios. Many products and programs either require or mandate a core framework and must be implemented on every hardware set. SatCom offers an optional SCA-compliant software stack using a core framework from CRC Canada, the Communications Research Center, and Corda middleware software from OIS. SatCom also supplies an SCA board support package that contains the logical devices or software-based proxies of the hardware elements that help abstract details of the hardware from the waveform itself. So if there's one message to take away from this slide, is that this robust software environment offers radio developers as much choice as possible when it comes to interacting with your underlying hardware and maximizing portability of the waveform. On this slide here, I want to touch on an emerging trend that what many can see in the communications equipment industry, and that is the trend towards developing multiple standard terminals or radio systems. If you are responsible for evaluating COTS hardware platforms, then you need to first evaluate whether the platform can support these other waveforms. One of the key strategies at Spectrum has been to work with many partners, such as Gatehouse, who have already implemented or in the process of implementing the following communication protocols and waveforms on the SDR 4021 platform, or Spectrum platform. Some of these waveforms include government and military waveforms, such as the UHF SatCom waveform, and JS waveforms, such as wideband networking, OSDM PHY, and physical layer for the SRW and SYNCART. Commercial protocols are standard, in addition to Inmarsat BGAN, that have been developed on the Spectrum platform, include public safety waveforms such as APCO 25. We have partners looking at doing TETRA and implementing the DVB standard. These are just some of many waveforms that have been implemented or are being developed on the Spectrum platform. So I'm just going to briefly hand it back over to COTS to talk about more about some of the specifics of the BGAN setup.
Thank you, Cyrus. This is a block diagram that shows the terminal which we've built. And the very central element is the Spectrum SDR 4021 platform, which is down here. Now we're connecting to the L-band converter. We're actually receiving a 10 MHz reference signal from it, but we're interfacing to it with our 70 MHz intermediate frequency, which we generate out of the Spectrum platform. And we feed this low power signal to the antenna interface, which feeds our antenna together with a DC power supply. Basically, Ethernet connections out of the platform, out of the Spectrum platform, and we connect to an Ethernet switch, which in turn to the converter for programming it. It also connects to computers out here for the applications, for the payload, and also development tools, debug terminal, trace tools. We also connect to a COM port server because we need to generate COM ports to be able to connect to our USIM reader and also to the antenna interface up here. Now this is a photograph of the prototype, and it's recognized again on the top part here, the Spectrum platform. Our L-band converter is a new tech converter, and we have our antenna interface, our radio front end down here, and that's necessary because we need to make level adjustments. We need to amplify the signal in the transmit and receive direction to feed the antenna with the right signal levels. And we also need an intermediate frequency filter, and we need the power supply for the antenna as well as the communication module for the antenna. So this is how the prototype looks. So what's the current status? We have ported our waveform last year to the Spectrum platform and did final waveform development in the period. We did testing with Inmarsat to achieve a preliminary conditional case approval from Inmarsat to allow us to go on air for one specific purpose, which was the SDR Forum 2009 in December. On them we gave a live demonstration of the equipment, and to reach the required level of performance, we had to do mandatory test requirement testing. So we were on the bench testing the physical layer and the protocol layers in advance. We also did on a test on an Inmarsat test network, and of course on the original network before we went over the Inmarsat the forum. What we showed at the forum was a fully functional BGAN terminal, running as any other BGAN terminal. We showed different applications there. Streaming video. We showed FTP transfers to show the stability and the performance in terms of data rate equipment, and we also showed general browsing to show more interactive kinds of applications. And it worked very well for the 4 days of the exhibition. Taking a look on at the future work that we are planning to do, we will include a channel equalizer into the waveform, which is required for aeronautical usage. We also plan to include circuit switch features. The prototype is supporting packet switch features at this time, data communication. So we plan to upgrade waveform with a voice codec and an ISDN stack. And we will also do additional MTR testing to generally increase the level of the waveform in terms of Inmarsat approval. Considering at the moment to go for a case approval, which is at the higher level, actually be able to allow for on-air usage of this equipment for manufacturers, able to operate the equipment and develop on the basis of our equipment without Inmarsat gatehouse or spectrum involvement. And with this, back to Cyrus.
Hey, Doug. So to answer the question, what else can you do, or what can you do with the BGAN-enabled SDR platform, and who can benefit from it? Well, one set of target users are folks who are doing waveform development, and these users include commercial satellite service operators, or commercial military SatCom radio developers, even research organizations, universities who are developing key waveform IP and components. And some of the edge to these kinds of users include being able to develop specialized application or network layer enhancements to the waveform or to their network standard, all through software. And all the while being able to reduce their hardware investment by reading the same hardware platform for multiple waveform development efforts. The second scenario is for users who are in the area of testing and spectrum monitoring. And these target users include test equipment manufacturers, or manufacturers developing spectrum monitoring or signal intelligence equipment, or SIGINT equipment. Some of the messages for these users include being able to, at least for test equipment providers, who provide test equipment to work with different air interfaces such as Inmarsat BGAN, is that you can avoid or minimize the amount of over-the-air testing by emulating the air interface of the Inmarsat BGAN network, thereby avoiding a lot of the expense associated with that. Another advantage is to be able to use a common SDR hardware platform that can be used across multiple products and work with multiple air or waveform standards, and having equipment that can be reconfigured at the factory or in the field. So this is a lot of benefit for customers who are using a lot of this test or spectrum monitoring equipment. The third area that we have is for developers of fielded terminals or radio. So radio developers and system integrators can use a SDR BGAN-enabled platform to develop and deploy using the same hardware platform. Also develop very unique hybrid terminals or multi-standard radio products that can support Inmarsat BGAN and other terrestrial or SatCom waveforms, and all those waveforms we mentioned in the past. And so the key elements, again, as I mentioned, is being able to develop on an SDR platform. So this is good here to be another example of a typical development platform that Spectrum can offer. And we can work with customers to deploy to something that is more suitable for deployment and rugged. And this example here is an ATR chassis, the kinds of chassis that we have worked with other customers in the past for their radio program. The end of the webinar, and we'd like to summarize a few key points. First of all, we hope you have gained a better understanding of the capabilities of Inmarsat BGAN, its complexity, and the amount of effort that was involved in developing and implementing such a waveform. Surely now see how an off-the-shelf BGAN SDR waveform software can significantly minimize your development time and cost. So you can start development today with an integrated, over-the-air ready Spectrum gatehouse system that consists of all the hardware and software tools that you need, including RF and modem processing hardware, the BGAN SDR waveform, the proven software stack that includes the SCA, the time operating system, drivers, and API libraries, the development tools, and of course comprehensive support and training. And so you can deploy either on the same platform you use for development or engage Spectrum and Gatehouse to develop a rugged radio or terminal hardware that integrates BGAN SDR software that is customized to meet your specific needs and requirements. With that, I'd like to conclude this webinar and invite you to contact myself or Klaus directly if you have any questions or would like to discuss your SDR project. So I do believe we have some time for some questions. I'll head over to Catherine and Klaus. Sorry, Catherine and Jeff.
Okay, thanks, Cyrus. Thanks, Klaus. So at this point, we have about 10 minutes left, and we're just going to open it up for questions. So please feel free to type in any questions you have in the Q&A box on the right. I'm going to start with one question that we have here. One of you asked if we have a smaller transceiver. The SDR 4021 is a 19-inch 1RU unit, so he was asking if we have a smaller transceiver, so I'll have Cyrus answer that question.
Yes, that's a very good question, and for the purpose of the BGAN terminal, BGAN selected to use the SDR 4021, which is a 19-inch 1RU unit. Mentioned earlier, the actual unit itself is made up of regular cards, and they have smaller cards that are in 2U compact PCI form factor, so they're much smaller and can be embedded into a small package. We also have Spectrum has a line of cards which have integrated L-band baseband processing, which are around the same size as a 3U compact PCI card. So yes, to answer your question, we do have there are smaller transceiver units available. It just so happens that the SDR 4021 as a rack mount unit is quite convenient as a development and demo platform. So thank you very much for that question.
Great, thanks, Cyrus. I just have a couple of other questions. People are asking if they can get copies of the presentation and also panelist contact info. So absolutely, I will send out an email after this webinar with a PDF of the presentation and also the contact information.
And we have one slide here that just shows our contact information for both Cyrus, for myself, and Klaus. So feel free if you have come up with any questions after watching this webinar, feel free to contact us. Thanks for your time. And
I guess there are other questions, so we'll be here. Thank you very much for joining us today. And I will be in touch with you shortly with the presentation and any other information. Oh, there's one more question actually. Can you first explain the restrictions on commercial use of BGAN? Perhaps, Klaus, you can take that one?
I think that's a question for me, but Keith, I'm not sure I understand the question. So I will get in contact with you and we can continue the discussion separately, if that's okay.
We had one more question. How tasked is the DSP? Can the current task be retargeted to the FPGA?
Do you think you could say a few words about that particular question?
Can you repeat the question, because I can't see it here on the list? Please repeat.
So the question is, how tasks to the DSP? Can the current tasks be retargeted to the FPGA?
How the DSP task can be retargeted to the FPGA? Well, we have, as I said, we have most of the implementation actually done on the FPGA, but part of the process of doing the code for the FPGA with the HDL, we have our MATLAB algorithms, and we have also decode to base our FPGA code onto. So we will be able to, and we have also been doing so as part of our development process, we're able to move some functionality between the DSP and the FPGA, depending on the specific system, and to open up for optimization simply. I hope that answers the question.
Great, thank you. Here's another question. How can one find more information about the BGAN air interface standards? I might be interested in using the terminal as a BGAN emulator.
I can take that one. We do provide from Gatehouse testing product, and one of our products is the BGAN network emulator, which is a tool that enables to run it against the network actually without being on air. And I think that's part of the question here. We can continue the contact. I can provide more information on the BNE, and also the possibilities of actually using a terminal as opposed to the BGAN network emulator as a test tool. It's not possible. Sorry, it's not possible to find public information on the BGAN air interface standard. Most of it is proprietary Inmarsat information. So we'll have to go into a log to satisfy that request.
Thank you. So if there are no further questions, I guess we'll say everybody for joining us today. Thanks for your time, and we'll be in touch.
Ladies and gentlemen, this does bring us to the conclusion of our call today. You now may disconnect. Have a wonderful afternoon.